Hi, good evening, all of you. Voice is clear. If voice is clear, give a thumb symbol. Hello, my dear students. If voice is clear, give a thumb symbol. That means like. Hello, students. Audible to you. If voice is clear, give a thumb symbol. Right? Hi. Good evening. This is Brahmaya. Now, the topic is if charge is placed in a uniform electric field. So let us see. This is a uniform electric field. Uniform electric field. If I place a charge here, this is a positive charge. If I will consider the electric field lines are coming from this is positive, this is negative. You know, everyone, the electric field lines are in the positive charge, directed or divergent like this. That means this is the positive charge of the electric field lines direction, this is the electric field line direction. This is the negative charge of the electric field lines. So let us see, this is the negative charge. Electric field lines are converging here like this. This is converging. So electric field lines are like this, from positive charge to negative charge. If I place a positive charge here, these two are attracted. Sorry, not attracted, repulsed. So these two are attracted. So it experiences a force right. It experiences a force. This is the direction of the force. The P equals to, suppose this is the charge Q, QE. The P equals to Q. If I place a here is the negative charge, these two are attracted, these two are repulsed. So it experiences a force W equals to minus 3. That means here it has a force. So this is the why this concept I am very clear. If the charge is placed in a uniform electric field, it experiences a force. So let us see now. Now let us see. This is the electric field. If I place a positive charge here, it experiences a force. This is W equals to QE. Suppose this charge has a m amount of mass. So in this case, this is the force. We have to write W equals to QE. This is force equals to R into the force F equals to from the mechanics MA. It has an acceleration. So acceleration A equals to QE by W. QE by, that means it has a acceleration. So that acceleration equals to QE by M. I hope it is clear. Now, so it has an acceleration. For example, this it is moving with uniform initial velocity. For example, let us say this is the electric field. So like this is the charge is placed here. It initially it has a E equals to 0. Then after it is become the V. Then what is the final velocity? From this V equals to U plus A T. So initial velocity 0. then final velocity v equals to a p. So this a we have to substitute, then final velocity v equals to, right, qe by m into qe by m into v. This is the final velocity when charge is placed in a uniform electric field. I hope it is clear. Everybody understand now what I am telling here? I think all joined. Okay, now it is okay now. So this is okay now. So this is okay now. So let us see once again. I will repeat this. This is the electric field lines. Electric field lines. Right? The positive charge is placed inside the electric field. It experiences a force F equals to QE. This positive charge has a mass, right? So F equals to QE. So and also we have to follow the Newton's law, right? Any body moving like this, there is a force that is F equals to MA. This is also applicable here. F equals to QE, that is also equals to the MA. Now A equals to, A is nothing but acceleration. Acceleration A equals to QE by M. Acceleration A equals to QE by M. This is the acceleration of the charge for charge while placed inside the electric field. Right? So now this is the one case. Now we have to take a second case. This is the charge is placed initially, it has a rest. After that it is moving here. Initial velocity 0. After this is the final velocity. At that time we have to use a Newton's equation on the first equation of the motion. V equals to ut plus at square. That is given by the V equals to at. Because of E equals to U equals initial velocity 0. Instead of the A, I will substitute this equation here. A is replaced by the QE by M. V equals to QE by M into T. This is the velocity, final velocity. This is the acceleration. Now let us see here. What is the, how much it is displaced from, it is accelerating up to here, this move now, this displacement we have to calculate. Right. So the displacement is, so we have a second equation of the motion, S equals to ut plus 1 by 2 at square. So initial velocity 0. So ut term is going to 0. Then S equals to 1 by 2. A is, this is the A. Q E by M into T square. Q E by M into T square. Right? So this is the displacement. Now you have to see here. Right. So in this case, it has a displacement from this. S is directly proportional to the T square. Look at this. This is the one of the relation, one of the important relation. It is visible to you. If it is visible, give one. I think thumb symbols are coming. It is visible to you. Give a thumb symbol, ma. Thumb symbol or any other symbols. You have to represent, show it. Visible to you clearly? Okay. Thank you, ma. Right? So now you notice that if the charge is placed in a uniform electric field, it has an acceleration, it has a velocity, it displaced. Whenever any body which is moving condition, any body which is accelerating, so it has a kinetic energy. It has a kinetic energy. What is the kinetic energy? So kinetic energy 1 by 2 m V square. 1 by 2 mv square. So V already we got a formula. What is the V? V equals to, right, QE by m into T. QE by m into T. So we have to substitute this here. 1 by 2 m into QE by m whole square. Sorry, here also T is there. T whole square. Now 1 by 2 m into QE, right, we have to write individually Q square E square T square by m square. M square m get cancelled. 1 by 2 Q square E square T square by m. So this is the kinetic energy. This is kinetic energy. I hope it gives a clear idea of what I was discussed with you. Okay, ma? Right. So now I will rub this. You should be copy, ma. You will copy her. Otherwise, I will rub her. Tell me that. Tell me, ma. Andrea. Shall I rub her? Or you have to copy now? Okay. Now I will rub here. So let us see. Okay, here we have to discuss a little bit note 1, like as this is note 1. If I take a simple pendulum, so this is a simple pendulum. Let us see here. It has positively charged, right? It has a positive charge, right? And also same time it has a mass m. Right. In this simple pendulum, we placed in a uniform electric field. The uniform electric field is, this is the direction of the uniform electric field. This is the direction of the uniform electric field. So now notice that this is positive charge. Positive charge, definitely electric field is this is the direction. Already I discussed with you. So it is force experienced by the electric field, that is QE. It has a Q positively charged sphere or small body, so that is the charge is Q here. And same way it is also experienced mg also downward direction. Mg also downward direction. So let us here, it is F equals to QE plus mg, we have tried. F equals to QE plus mg, we have tried. And also this is a tensional force which is experienced here, right? Tensional force. So let us see, which is we have to write, otherwise I will write here regarding the F net equals to this, it is hanging, so that's why it has a tensional force T minus QE plus mg, we have tried. T minus QE plus mg, we have tried. Okay now? It is okay, ma? F net. So now, if I take this is, in this case, we have to take sorry, net force only we have to take T equals right? In this case, it is accelerated downward direction. So for this case, it right. I think it is. Hello, it is okay, ma. What I am telling, understood? Once thumb symbol, ma. Thumb symbol. Hello. So here, what I am taking, this is not. So let us see. Net downward force. F net equals to QE plus mg. QE plus mg. So here this is force. I wrote in the form of G. That means I will write here mg effective. That equals to QE plus mg. Then G effective equals to, like this m is going this side, so QE by m plus G plus G. This is the net effective. So it is oscillating. The time period will change. How it is changing now? Because of it is oscillating due to this electric field. So it is, the time period is, so we have to write 2 pi root L by G. This is the G effective, right? T equals to 2 pi root L by G effective. This is, right? QE by M plus G. QE by M plus G. This is the acceleration of a simple pendulum. The electric field is downward direction. It is a positively charged. Instead of that, if I take a negatively charged, what will get it? Okay, ma? Right. So now one more. We will discuss one more. So let us see. Okay. Shall I rub this? See here, another one I will take here. If I will take here, this is simple pendulum which is having the mass m. So this is the initial case. So in this case, if for example it is hanging like this, in this case electric field is, this is the direction of the electric field. This is the direction of the electric field. So due to this electric field, it is a positively charged. It will move, shifted like slightly like this, slightly like this. Due to this electric field, it experiences a force. This is F equals to QE. This is mg. F equals to mg. We have tried. Okay, now. And now, so let us see. This is the one of the force. This is the another force. The resultant force should be act like this. This is the resultant force. F net equals to, we have to write root of, because of these two are 90 degrees. So F net equals to root of QE whole square plus mg whole square. So if I write here regarding effective acceleration, so mg effective equals to root of QE whole square plus mg whole square without right. This m, this side will, right? So like this, see here, QE whole square, so plus mg whole square by m, by m. So I will send m inside. Then what happened? G effective equals to root of QE by m whole square plus, this is m get cancelled, G square. So then time period of the simple pendulum is 2 pi root of L by G effective. So now T equals to 2 pi root of L by G effective is root of QE by M whole square plus G square. This is one of the important note. I think it is clear, right? Okay, ma? It is okay now, visible to you? If it is visible, give one thumb symbol. If it is visible. Okay, now here I have to discuss one null point concept, electric field due to null point. Okay. Right, so let us see. This is null point, this is positive charge, this is negative charge or positive charge, whatever it may be. Due to this, there is a electric field between these two. Right. Suppose if I will take a electric field here, because of if I will take a Q, it experiences a force. That force per unit charge is called the electric field. Right. Here, if I will take this is the positive charge, this is the negative charge. In between, there is a null point. That means electric field is this is the electric field direction. Right. Because of due to the positive charge, electric field direction like this. Due to the negative charge, electric field direction is like this. So let us see it. In this case, null point, right, outside of the sphere, it will exist outside of the sphere because of electric field. And now if I will take this is the positive charge, this is the positive charge. In between, electric field is null point is here only because of the electric field due to the positive charge, this is the direction. The electric field due to the positive charge, this is the direction. So null point kandipa here only. Right. If opposite charges, null point outside, either here, either here. That is depends upon the magnitude. Same charges, null point kandipa between. Either this is exactly middle means these two are same charges. That the magnitude of the two charges is same middle. But either it has the maximum, it has the minimum, it is variation is there. And one of the important here I will discuss, that is electric field lines. Electric field lines, one of the important topic, electric field lines. What are the electric field lines? So let us see. Already I told you, this is a positive charge. Electric field lines are imaginary lines, right? So which are represented the electric force of lines. Electric force of lines. These are the imaginary lines. So positive charge, the electric field lines are diverging like this. Right. Negative charge, the electric field lines are converging like this. And if I take this is a positive charge, This is the positive charge. What is the electric field lines between these two? So positive charge repels. The electric field lines are like this. So if you draw continuously like this, there is a point here, middle. This is called the null point. This is called the null point. Right? This is one of the important. And the next one is, if I take a, this is positive charge and negative charge. Electric field lines are starting from positive charge, ending at negative charge. So let us see here. Electric field lines are starting at positive charge, ending at a negative charge. This is the representation of the positive charge and the negative charge. And now, here you have to see the electric field lines start from positive, end at negative. So, electric field lines are not closed loop, because of it is starting here, ending here, ending here. So it is the starting point, ending point. So different points are there. It's not closed loop. It will not form the closed loop. And the next one is, second point is, any two electric field lines are not intersect. Not intersect. So why not intersect? Suppose if you take it, this is the one of the electric field line. This is another electric field line. If these two are intersect here, it should be has, this is the one of the direction, it is another direction, but it is not possible. It is not possible. According to the vectors rule, it is not possible. It should be go like this. According to the vectors rule, this is the one of the vector, this is the another vector, the resultant vector, like this is the direction. But it is not possible. It should be go like this, it should be go like this. So that's why any two electric field lines are not intersect. I hope this is enough. Right? Maybe tomorrow it will be continued. Okay, na? Right, ma? Purida, what I am telling to you, what I am discussing with you. Okay, na? Right? Okay. Tomorrow we will discuss, ma. I think it is time is 9 o'clock. I think so. Okay, na? So who are watched? Put a WhatsApp comment in WhatsApp. Thank you.